welcome back to section 11.7. The next thing we're going to look at is maximum and minimum application problems. So in general, sometimes our parabolas, they're upward facing, and sometimes our parabolas are downward facing, kind of like that. So when it's an upward facing U, that vertex point right here, the vertex, is the lowest possible value or the lowest possible y value, so it's a minimum. So when it's like, hey, what's the minimum, whatever, it's looking for the vertex, and it's an upward shape U. If it's a downward shape U, that vertex is the largest y value that you're ever going to get, and so when it's a downward shape U, that vertex is going to be a maximum. And so when it asks you for the maximum something, what they're really looking at is the vertex, okay? Sometimes for the vertex, they're looking at the x value, sometimes they're looking at the y value. So you do have to pay attention to the context of the problem to figure out which one they're looking for, just to figure out in the context of the problem, what is your x and what is your y, okay? So let's work through some of these. So the first one I have in example 4. A farmer has 100 feet of fencing. He wants to put a fence around a rectangular field next to a building. Find the maximum area he can enclose and the dimensions of the field when the area is maximized. All right, so I'm a very visual person, so I just like to at least sketch something out. So apparently he has a building. I'm just going to put a B for building. And then he's going to put a fence next to the building. I'm going to assume that he's not going to fence alongside the building because it's already has a boundary there, which is the building. So this is kind of what's going to happen is he's going to have fencing along those 3 sides next to the building, and he doesn't need fence along the building, right? So then what's going to happen? Let's see, he's going to have 2 lengths and a width basically to deal with fencing. Let's see, he's got 100 feet of fencing, so that means that if I add those 3 sides together, that should equal 100 feet. Since he wants to maximize the area, I assume that he wants to use all of his fencing, because if he used less than that 100 feet, it would not give him the maximum area. So if I add all those sides together, there's 2L, so 2L, and then we'll add the width as well. So adding all 3 sides together, that equals my 100 feet. That's what I know so far. Let's see, he wants to maximize the area. So I know the area of a rectangle equals length times width. So those are my kind of starting equations, okay? Now you'll notice that we're trying to maximize area, but we have 2 different variables in there. That's why we need this other piece of information so that we can just get an equation with 1 variable instead of 2. So what I'm going to do is I'm going to take this first equation and I'm going to subtract 2L from both sides. So then I've got W equals 100 minus 2L. So then I can substitute. So in here where there's a W, I know that W equals 100 minus 2L. I can substitute that into this equation and then have just 1 variable. So now I've got area equals length times 100 minus 2L. And I think I can simplify that a little bit. Let's go ahead and distribute. Area equals L times 100, so that's 100L, minus L times negative 2L, so minus 2L squared. And if I want, I could also rearrange that so it's in standard form, since we've been doing everything in standard form. This has the higher exponent, so I'm just going to put that first, negative 2L squared. That has the next highest exponent, so plus 100L would go second. Okay, so now I've got one equation that has like L's instead of X's and A's instead of Y's, okay? That's basically where I'm at. So, and you'll notice it is quadratic, it is going to be a parabola. It is a negative A value, which means it's going to be a downward shaped parabola if I were to graph it, okay? So when he wants to find the maximum, that's the biggest right here, the maximum area is going to happen at the vertex. So really what I'm trying to do is I'm trying to find the vertex of this equation, okay? So I'm just going to use my easy equation here and say for my vertex, so my vertex is going to have an L value for the x's and an A value for my y's, just so that we're clear. what my variables are and where they are going to be in my point here. My vertex, let's see, my x value, or my L value in this case, is equal to negative b over 2a. Well, negative b, we don't even have a c, in case you were wondering. We have an a value of negative 2, we have a b value of 100, and our c value is 0. We don't have a plus anything at the end. So our opposite of b would be the opposite of 100, which would be negative 100, over 2a. So 2 times negative 2 would be negative 4. And then if I simplify that, negative 100 divided by negative 4, I'm going to get positive 25 for my L value of my vertex. Okay? Then if I want to get my A value, all I'm going to do is plug in 25 for L. So my maximum area is going to happen when L is 25. So I'm going to do 2 times 25 squared plus 100 times 25. We're going to get some big numbers. It's going to be exciting, okay? So if I do 25 squared, I get 625. And then if I do 625 times negative 2, whew, goodness. So let's see, 625 times 2, I should know this. 2 times 5 is 10. 2 times 2 is 4, plus 1 is 5, and 2 times 6 is 12. So it'll be a negative 1250. 100 times 25 isn't too bad. That's 2,500. Okay? And we have a negative plus a positive, so really we're subtracting. So if I do 2,500 minus 1,250, we get positive 1,250. So our area is 1,250. And so really, if I put those two things together for my vertex, the vertex is at the point 25, comma, 1,250. Okay? So answering the question, let's see, find the maximum area he can enclose. Okay, well, the area, we have that. It's 1,250. Let's see, everything was in feet, so that would be square feet for our units and area. There's your maximum. Find the dimensions of the field. Well, we figured out the length. The length was 25 feet, right? So length for our maximum area would be 25 feet. And then to find our width, we're going to go back up to this little equation. Width equals 100 minus 2L. So 100 minus 2 times 25. 2 times 25 was 50. 100 minus 50 would be 50. So for my dimensions, for my width would be 50 feet. And the nice thing is you can even double check that area with this length and width and do 25 times 50 and you'll get 1,250. And so that's a nice little check for you as well. All right, let's do another one. Example 5 says between 1989 and 1998, the population of small-town USA in thousands can be modeled by this equation. So they give us the equation f of x equals 0.82x squared minus 11.48x plus 48.2. Probably somebody did a lot of statistics and modeling, and they looked at all the data points and plotted a nice little curve to represent that data. All right, and just letting us know here, let's see, the f of x is going to be our population in thousands. And x equals 0 represents 1989. So basically, those x's are going to be the years since 1989. So like x equals 1 would be 1 year later, which would be 1990. X equals 2 would be 2 years later, 1991. Okay, so that's what that means. Based on this model, in what year did the population of small town reach its minimum? You'll notice that we have a positive a value, so this is an upward shaped parabola. So the minimum happens at the vertex, the very bottom point. Okay, so yet again, we are looking at the vertex, okay? So for our vertex. Let's see, the x value, what we're going to do is negative b over 2a. So the opposite of negative 11.48 would be positive 11.48. 2 times a, you do 2 times 0.82. Whew. All right, so let's see, 2 times 0.82 is 1.64. And if you do 11.8 divided by 0.64, you actually get a perfect. It's 7. It divides out really nicely. Okay, so what that means is 7 years since 1989 was that minimum value. And so if I take 1989 and add 7 to it, I'll get the actual year, okay, that we had our population minimum. And so 1989 plus 7 would be the year 1996. And that is the only thing it asked for. It didn't ask for what the minimum population was. If it did, you would just plug 7 in for x into the equation. You would not plug 1996 in for x because that's not the x value. 7 is. If it asked for that population, you just substitute that in. But they only asked for the year, which we can get from the x value, and do a little bit of additional math for it. Okay? Now it's your turn. You guys get to try one and show me how much you've learned.